So this session is all about AI for good. How can we use AI to accelerate what we know about the world, what we know about ourselves? And to kick things off, I want to start by asking our preeminent panelists, what is really AI for scientific discovery and what it enables? Because we've had simulation, we've had statistics, we had supercomputers for a long time. And so what is new with AI in scientific discoveries? And what fundamental new kinds of questions can we ask? Okay, don't be shy. Jump in.
Oh, yeah. Okay. So I'm Andrew White. So what is new for AI in science? I think the methods you described there, like simulations and using supercomputers, they've driven a lot of, I would say, like the theory into like practice. But what we can do with AI now is we can actually predict things driven from data. And it also allows us to bridge the fields because language is sort of the universal connector in science. Basically, we worked together for thousands of years on making language represent the physical world. And every time there's a new concept scientists discover, they attach a new word to it. And that has given us this really new power that the language models can actually bridge them all. But I think language models is not, the only part for AI for science. And I think there's a lot of other work in the last 20 years, 30 years, maybe 50 years on using different parts of the AI theory in things like protein folding, which was not language model based, or just, even regression has been a powerful tool that, a lot of it came from machine learning when we went with the neural network. But anyway, that's just a little bit about it.
So
I think if you think about scientific discovery, much of it evolves around looking at data and trying to make observations from the data. That's not the only way scientific discovery occurs, but that's really an important part of the scientific method. And one of the great observations about AI is it's very good, and this may sound simplistic, but it's very good in finding patterns and observations from data in ways that people have not been able to achieve. And so I think one of the great benefits of particularly quantitative AI is that you'll be able to take data that has been collected over long periods of time and find interesting things in the data that people in the past have not been able to observe.
So we have a lot of powerful models. We have multimodal models that deal with all kinds of data. Are we done, or do we still have some challenges that need to be addressed?
Yeah, so we have really a lot to address. The way that I like thinking about the scientific discovery is that current today LLMs or generative AI really is about learning what we already know, which is the internet data, which is the artifact of human knowledge. Now, is that the entirety of knowledge in the universe? The answer is often no, because I think there's a really universe of knowledge that's just so much more vast and bigger than what we know as a human about the world. So, how do we cure cancer, or how was the universe created in the first place? And what is dark matter? What do they really look like? And all of these are unanswered questions that require almost like leap of faith. And current day AI is only really good at remembering, memorizing, learning the patterns of the internet data. Now we need to find a way to make the AI to be able to find new knowledge for us.
Go ahead, Arti.
I think one of the things that maybe with the advances of LLMs and kind of transformer-based models, we sort of think about AI in one specific way, which is like, let's build these very large, generalized models, often that, are text-based by nature. My background, though, is in astrophysics. It is in actually studying the dark matter and origins of the universe, and now I work in the industrial space. And in both of those areas, I worked with a lot of time series. So I used to work with time series as an astrophysicist to kind of identify different types of, and identify and classify different types of astrophysical objects that were time varying. In the industrial space, time series are critical to understanding the behavior of turbines, power plants, anything that keeps the world going. this is not a well-solved area right now. Really understand. I'm sure David understands this from the financial sector, but what are zero-shot ways of modeling time series and getting good forecasts and anomaly detection from any generic time series? That's not a well-solved problem. The best ways to solve it, though, are with older machine learning methods, but then you need a very good data scientist that can go through and figure out what is the best way to model a time series. So, this is an old problem in some ways, but still one that, from my perspective, is very much not solved.
So do we need models that fundamentally understand time series?
So this is a great question. My team has been looking at, there's a number of time series foundation models that have come out over the last year and a half, and we've been looking at how well they can perform in industrial settings. I don't know. I mean, do we need time series foundation models? Often we might want to be using them in areas where we want kind of more parsimonious, frugal energy use of AI. So maybe we don't need a foundation model that can work for everything. We need to somehow standardize or come up with a more automated way of figuring out what the right model is for a particular time series.
There's more to AI than essentially large language models and the foundation models that most people here at Davos are talking about. Machine learning in general is advancing as well. The ability to, for example, incorporate world models into essentially the physics of a problem into a large language model or even into machine learning is another area of advancement. And so when I think about AI for science, I'm thinking very broadly about a set of methods that is actually quite diverse, and that's where I get most excited. I think it's very likely that combinations of generative AI, quantitative AI, are actually going to unlock tremendous scientific potential.
Oh, absolutely. I think
maybe I could go on your foundation model part.
Okay, go ahead.
So although foundation models have a lot of limitations because at the end of the day, it's a pattern learning model, I do think that we have to invest a lot more on building foundation models for science, because compared to where things are with LLMs, we don't even have ChatGPT of foundation models for science. I don't think we even have GPT-3 yet. We might be somewhere between GPT-2 and GPT-3. So a lot more work to be done.
So let's see, Yejin, earlier today we were talking about some of the challenges that have to be solved at the technical level, namely continuous learning and in situ adaptation. So can you talk about that a little bit?
For sure. So I've been quite thinking a lot about how to transcend the limitation of current day of doing LLMs. And one critical concern for me is that it's not able to do continual learning, especially during test time. The scientific discovery requires, even after being deployed, the model has to be able to learn from its own reasoning, which can be extremely long, and then it has to learn from its own trial and errors, which essentially requires test time training. Now, this notion, test time training, sounds almost wrong to us because machine learning 101 tells us to completely separate out testing from training. Mixing the two is almost a sin. However, humans, even from day one, when we are born, we're deployed in the real world, and then we are always in the test mode or deployment mode while also learning and training ourselves. So I think the future of AI should really think about how to make AI to learn and think for itself from day one in a more proactive manner.
Let me comment on that in talking about how humans learn. And I think many people understand it's not a great idea for people to essentially learn how to take a test. So if you simply learn how to take a test, you might be really good at getting a high score on a standardized test, but you may not actually be a creative thinker. You may not be able to solve problems that didn't appear on the test. So currently, most AI models are essentially trained to benchmarks. You probably all heard that. And like a benchmark for humans might be in America, we take the SATs. That's a benchmark. The LSAT is a benchmark for getting into law school. And so AI systems have to be optimized against something. And in general, they're optimized against these sorts of, whatever the benchmark is. That is not the optimal way to get the models to be creative. And so one area of research is, well, how do you build these models on something that's more vague and is not something that is easily benchmarked, like creativity?
So that's a very good point, David. And it's really interesting to think about how we should look beyond standard AI metrics to measure whether AI is generally accelerating scientific discovery. So how should we think about that? Any ideas?
Yeah, this is something we struggled a lot with at Future House, which is a nonprofit I founded, and then Edison Scientific. We build benchmarks, and if you go look in the Frontier Models appendix, their system card, the benchmarks we built for science are often shown there. But this question always comes up of how do you know it's a new discovery if it's in a benchmark? And this is actually a really difficult thing to retrospectively assess if you've made new discoveries or if you're being creative. So what we did is we tried to measure the full end-to-end system. So we work with academic groups, including from Stanford and MIT, and we asked them to withhold data and papers that they were working on at the time. We wanted to see if we could recapitulate the same discoveries that they made from the data. And we were able to do this in 7 examples. 4 of them, we were able to reproduce the same discovery they made in fields like material science and genomics, and 3 net new discoveries, including one on why the entorhinal cortex, which is part of the brain, is uniquely vulnerable in Alzheimer's and other neurodegenerative diseases. So real stakes for these discoveries.
So just a quick follow-up. In your vast experience with this end-to-end solution, what have you learned about what these systems are good at and what they're bad at?
Yeah, so we took the things that came out of our system, it's called Cosmos, and we break up the report. They come up with the claims and why they're supported. We give it to PhD experts in the field and ask them to assess which of these claims are correct. And we find that humans can reproduce the claims about 85% if it's about writing code. They can reproduce this claims if it's about interpreting figures from a patent or from a research paper, about 80%. But when it comes to agreeing with the importance of a claim, humans say they agree about 50% of the time. So the biggest gap right now is what we call internally scientific taste, which is how much these LLMs understand the significance of a discovery, if a discovery is interesting, and if they've done the right sort of supporting evidence for it. So I think that's the kind of frontier right now in AI for science, is imbuing these models with an ability to assess if something is an important discovery and if it's sufficiently supported that you can, claim it. So I think that's where we're focused on right now.
So I have another quick follow-up. Do you ever have one of your AI scientists get off the track and get really stuck on the wrong hypothesis? How do you detect that, and what do you do?
Yeah, this is actually another really difficult thing is we wanted to build something fully autonomous. So I think there's a lot of people building AI and they really want to have a human in the loop kind of process. We wanted to see if we could have something fully autonomous. So you launch our AI scientist, it will run for 12 or 24 hours. It will consume 10 million tokens. It'll write 75,000 lines of code, read 1,000 papers. And sometimes it will just go on the wrong track. It will go down a rabbit hole and find something that's totally uninteresting or something totally obvious. And, you just blew whatever, a couple $100 on compute on this. And we're trying to find out how to get a human scientist to participate in the process. But if we let the person drive it, we find that we don't get the more interesting discoveries that emerge out of it. If we let the AI drive it by themselves, they get to these rabbit holes. And so we really haven't cracked this problem yet. But I think this is one of these things that comes back to, can you get scientific taste? Can you train on it? Can you build a benchmark of, what is a good discovery? What is an uninteresting discovery?
So, Arti, you sit at the intersection of your training in astrophysics and now working with industrial systems and critical infrastructure. Where do you see AI for science methods actually making it into factories, energy systems, process industries?
Yeah, that's a great question. And, I mean, maybe I'll also address your previous question as a lead up into the answer for this, because, we're talking a lot right now about like kind of AI for discovery, where AI is essentially doing the discovery. But there's another way to think about how AI can advance scientific discovery, which is the other ways it might enhance the work of a scientist. And so, I also have worked in high performance computing. And, you mentioned simulations at the sort of outside of this panel. And the ways that AI has enhanced our ability to leverage simulations, large simulations in science is just, been radical over the last decade, whether that's taking like very large physics-based simulations and replacing portions of it with AI in order to, get simulations to run faster. This has led to being able to get climate models to converge faster, or also leveraging AI to make a decision around I'm running a large ensemble of simulations, and maybe it helps me explore the parameter space better, like decide which ones to run. Because even if I can run a large ensemble, there's still only so many runs I can do. And so one example of how like one of our customers is using that in the industrial space is we provide process simulation software. So to understand how processes will run for chemical manufacturing, molecular, any kind of manufacturing systems. And so we have a customer called Covestro that was looking to design new bio-based polymers. And what they needed to, there's one area you can use AI to sort of discover new molecules, but then they had to figure out which ones were going to be commercially viable. And so then they used AI along with our process simulations to figure out which ones they could actually run energy efficiently and cost effectively.
So let me move.
I'd like to actually amplify that point, because I think, and this was not really apparent to me until it was explained, in many fields like material science, drug discovery, chemistry, development of catalysts, the success rate of the ideas is critical. And so, for example, in chemistry, most of the, for example, catalysts that people are trying to develop don't actually work. It could be a failure rate as high as 95%. And same in drug discovery. So if AI could simply reduce the failure rate by just a couple of percent to take, the number of trials that work and take it from 2% to 4%, you've just doubled the productivity of all the scientists. And that doesn't sound like a big advancement, but it's huge for the fields.
It's huge in industry and it saves a lot. I would like to move the conversation from industry to academia. And I want to come back to you, David, because you have been very engaged in supporting academia with resources that enable researchers to pursue AI for scientific discovery ideas. Can you tell us a little bit about your project, your Open Athena project?
I'd be very happy to. So one of the challenges, and this is really a global challenge, is much of the world's basic research comes out of universities. Universities are actually critical for the ecosystem that creates industrial innovation. The difficulty that we have right now is that basic research in the past has been done in a very traditional way. These days, it's becoming much more software intensive. So to properly use AI in a university environment, you need a lot more technical software capability. Universities don't generally have this. You need the kind of software engineers that a firm like Microsoft or OpenAI would employ. And to address this, I've created a foundation, Open Athena, that essentially is a professional software engineering organization. We're hiring AI engineers, and we second them to academic projects to allow the academic teams, maybe in astrophysics, to more rapidly deploy AI techniques on their scientific projects. My big concern for the university scientific world is that they're going to fall behind because they won't be able to deploy these new emerging AI technologies fast enough.
Well, I believe in the human creativity and ingenuity, and I think that we need new ideas, and universities will continue to generate the new ideas. But without the research infrastructure that you're talking about, it's going to be difficult to get an idea from like a baby step to show real impact.
Yeah, the world has moved much more in the direction where you need more and more essentially software engineering, and especially in an AI-centric world, and that's the problem that I'm helping to address.
Yejin, so you've made so many contributions to AI from your university position, and you really worked extensively on common sense reasoning, and that this is very important because we all know that transformers don't have embedded common sense reasoning, and common sense reasoning is very important for language. How important is it for scientific discovery?
Yes. Actually, transformers these days are pretty good with the common sense, I would say. But it's true that, when language models at very large scale, such as GPT-3 was first introduced, or even GPT-4, they did make more common sense mistakes. Now, the way that issue got addressed is quite curious and relevant for AI for science for the following reason. The way that us humans acquire common sense is a lot more internalized and a lot more independent. We just figure common sense out without the need for extensive post-training through a lot of common sense exam problems. Whereas AI, today you have to feed that in. So in the context of AI for science, if we just follow the current track, that's exactly what we need to do for, for example, molecular synthesis, molecular reasoning. Maybe, it's a common sense for chemists that certain chemical reactions are toxic or dangerous or impure. And injecting all of this knowledge requires a bit more direct and explicit data preparation as of today. But the thing about AI for science is that science does not have internet data. All that they have is some kind of scientific data that is somewhat unevenly collected, which means it's not going to be able to cover all the common sense knowledge of scientific fields. So as a result, either we need to solve the data problem, or we need to fundamentally change the learning algorithms such that it can really acquire, almost like reverse engineer, the common sense rules of how the world operates at the molecular level or at the cosmology level.
Yeah, so that's super interesting, and I can't wait to see how that work unfolds. Another aspect of scientific discovery is the physical world, and it's making predictions in the physical world. So I wonder what all of you think about two aspects of this problem. First of all, physical systems have a lot of messiness associated with them. How do we integrate that messiness to get robustness from the performance of the AI systems? And then how do we move beyond prediction? How do we close the loop from prediction to actual experimentation and back to hypothesis generation?
Well, so I'll start, as a physicist, I think one of the things sometimes we forget is a lot of our knowledge of the physical world, things we take for granted as sort of now laws of physics, they came from observing the physical world and collecting a lot of data and sort of, teasing out the kind of essential laws that govern the messy things you observe in the world. So, when I was still like a data scientist and I earned my living by actually analyzing data. I used to work at a large industrial, and I would take some data from like jet engines, and you would be shocked at how often I rediscovered Bernoulli's principle. So, I think that, it's a good reminder that like physics sometimes is very good, and the things we know about physics are very good. I think right now there's a lot of work being done, physics-informed neural networks. How can we take artificial intelligence methods that are more kind of data, empirical and data-informed, and combine them with what we already know about the physical world, because then you can get maybe, better understanding of things you don't have good physical models for, or like if you're seeing something diverge from that, that's quite helpful. So
I'm so energized and inspired by everything you all shared, and I would sit here forever to talk with you, but we're almost out of time. So rapid fire, what is your favorite AI for scientific discovery problem? Artie.
well, I guess I would say right now I'm very interested in how you can understand how to take simulations of things and use them to operate stuff in the real world. That really forces us to understand a lot more about processes than we know right now.
Andrew.
We wrote a paper in June where we wanted to know, can we cure a disease with our AI system? So we put in a disease, dry AMD, age-related macular degeneration, is why people go blind later in life. And it proposed experiments. We did the experiments. It analyzed the experiments. We did more experiments. It proposed more, and it was a complete loop. And it ended with a drug, which we have in animal models right now. It looked good in human cell donors, and I think, it'll take a few more months. We may have the first end-to-end AI-discovered drug.
Amazing. Yajin.
My wishful thought is to really solve all these, mysteries about human bodies and health and medicine, so that we can all live without illness.
I like that. I would like to reverse aging. David.
I would like to be able to simulate the brain of an ant. And, it's a pretty simple, let's figure out actually how it works.
Well, there are many young people in the audience, many students. I think you all got a wide range of exciting and important problems to work on. So let's thank our awesome panel. Thank you so much.